Thank you for joining today. My name is Elias Prunen. I teach one of the DABI courses as part of the WattSpeed program, DABI 2, which focuses on Python and public policy. The material that I'll be presenting today tries to build on Anodot's content, and we try to take a look at machine learning and demystify it. I, I've my background's in computer science. I'm a trained programmer. I also run a lot of events, do a lot of data consulting. I am not a trained statistician. I've picked this up over the years through a mixture of my own consulting, my own learning, and my role has mainly been in building out the data warehouses and the databases and the data load processes that the big brain researchers use to conduct their analysis. Through osmosis and a lot of generous folks, I have learned quite a bit about statistics over the years, but I'm not a trained statistician. I find my role is more in translating what are these ideas around machine learning and how can we use them in the real world. So today's content is going to be focused a lot less on the theory and the mathematics behind the models, and they're going to be focused more on application of those models. So with that said, let's move right along since our time is limited and start out by anchoring our discussion in what machine learning is. So what is machine learning? Well, let's ask ChatGPT. And I think in this case, it came up with a fairly good answer. Machine learning, it's a type of artificial intelligence and allows us to learn or make predictions based on patterns and data without having to be programmed for each scenario. And I want to call attention to the three key points. We're making predictions using data to make those predictions, and we do not need to make code for all the different possible output scenarios. And this is very different from your traditional programming model. So in traditional programming, we would write a bunch of rules into some sort of a system, and we would get the same result based on the same inputs. For a given set of inputs, we will always get the same results. For example, I was working on a customer relationship management system a number of years ago for a Fortune 500 bank, and they wanted to rank out of 5 stars what the likelihood was that a particular opportunity would close and become a closed won sale. And what we were doing is saying, if we've had at least 3 meetings and they have buyer's intent and they have positive reception to the product and the opportunity size is over a certain dollar figure, then rank this as a 5-star. And then for each feature that we were missing, knock down a star until we get 0. So for a given set of inputs, we would get a output of 0 to 5 stars for every single opportunity. And that was hard-coded in the system. The downside of that was, even if we had an opportunity that on paper, on this coded system, looked kind of fringe, we didn't have a way to account for the fact that this opportunity has the CEO involved. And because of that, even though it's a large deal size and we don't have a lot of meetings, it is quite likely to close. Yet that deal was ranked as a 1 or a 2-star. So we didn't have a way to account for these other issues without having to go. If we wanted to account for these other properties, we'd have to go back in and modify the system. This is where machine learning could come in. So for example, with machine learning, we can throw a bunch of data at the computer, have the computer analyze this data, and take a look at the results it comes back with, and then tweak those results to say, actually, you think this is a 2-star deal. This should actually be a 4-star deal because X, Y, and Z. And so the predictions that we get out of the machine can change based on new input. In fact, depending on what data we train the machine on, we could actually see different predictions given multiple runs. And we're going to see this once we get into building some of these models ourselves. So this is the difference between traditional programming and machine learning. Another way to think about it is With machine learning, we're going to be guiding the computer on how to make predictions rather than telling the computer how to compute a specific output. And I'm going to also plant a seed, which is I want you to think about this in terms of probabilities. We're going to be focusing a lot on the probability of an event happening or an event not happening. With computers, we're typically used to programming something and getting a yes, no answer. With machine learning, we get into more of a fuzzy output, a maybe, maybe not, which that can be tough for computers to deal with. It can be tough for us humans to deal with. We like certainty. Where is machine learning used? So in medicine, there's a lot of applications of machine learning today. For example, in lab and clinic settings, we're starting to see machine learning algorithms be used to reconstruct diseases. We are seeing it being used to make prognosis estimates for patients. We're seeing it being used in diagnostics, for example, diagnosing, given a set of photographs of a skin tumor. Is this a malignant tumor? Is this or is this a cancerous tumor? Can we determine that? And in fact, back in 2018, the U.S. Food and Drug Administration approved one of the first AI-based diagnostics in the United States to detect disease of the retina caused by diabetes. You can read all about that. I've linked I'll be providing these slides, and I'll be providing all code at the end of today's session, by the way, as we will be moving through the code at a brisk pace. So we're starting to see machine learning being used there. We're also seeing machine learning being used in commercial applications. For example, retail stores figuring out what products seem to be bought together. So if you've ever used a application such as Instacart or any of the other grocery delivery applications, you may see at checkout the recommendations of need any more items. And that need any more items is based off of uses machine learning algorithms to determine, oh, I see you bought eggs, but you didn't have milk in your cart. Well, we see that eggs and milk are bought together 80% of the time, or at least the data that we have shows that people in this demographic seem to buy milk and eggs 80% of the time. Let's recommend maybe you need some eggs, maybe you need some milk along with the eggs that you're purchasing. So we're seeing machine learning being used to find patterns in data and recommend and make recommendations. If you have Netflix or Amazon Prime or a streaming service, again, those recommendations are based off of the data that you are feeding those algorithms, your watch patterns. For example, when my family goes on Amazon Prime and uses my account and they watch a couple of Peppa Pig episodes with my 10-month-old, my feed gets filled up with childhood cartoon suggestions of things I'd like to watch, when really I just want to get back to my latest crime drama. And sometimes that gets a little bit awkward because nothing like being recommended Peppa Pig and then something about true crime. But these are some examples of where machine learning is being used. There are two major categories, two families of machine learning, and we're going to be talking about both today. The first we'll look at is supervised machine learning, where we are going to provide the computer with a set of labeled data. And when I mean labeled, I mean, say, for instance, we have a set of data of patient attributes. And for each row in this data file, we have attributes such as their weight, their age, their smoker status, and whether they're sick or not sick. So we feed this data into an algorithm, and then we try to make predictions on new unlabeled data and see how accurate those predictions are. The other type, which I find to be a bit more interesting, because I find it a bit more interesting than supervised. Supervised is awesome, but unsupervised machine learning, where we feed the computer unlabeled data. So for instance, if we fed the computer data about, again, patient characteristics, and then said, we then can ask it, find some patterns in this data. Let's divide this up into clusters and then see what is common to all of these clusters. So these are the two families of machine learning that we will cover today, and we'll be using Python to do both. Now, I just want to take a quick sidebar and talk about being pedantic about language in this webinar. In my DABI course and in any of the courses that I teach and in my consulting practice, I harp to great lengths about results. I don't like referring to the output that I get from a computer as an answer. I like to talk about results. What I found is that the moment you talk about an answer, that implies a certain level of correctness. And it implies that what you've been given, the output from the computer, we cannot question this. This is authoritative. And I am not comfortable with that. What I find is when we get the output from the computer, when we get our results from our analysis, that's where the real work starts. Because as Anado was talking about, computers are a tool that we can use to offload the work that we would have to do otherwise manually. We can shift that over to a computer, and that frees us up to do what we humans are great at, which is inference, creative thinking, problem solving. Those kinds of problems our brains are fantastic at. Computers are amazing at finding patterns in data. They're amazing at doing repetitive tasks. We human beings, not so much. The computers have us beat there. So when I refer to the output from our algorithms, I'm going to be talking in terms of results, because a lot of what we do in regression analysis, in logistic regression, in machine learning in general, a lot of this, we're in the land of fuzzy probability, and a lot of this is open to interpretation. So I'll be talking about results. I prefer not to talk about answers. After all, I am a consultant, and I love giving the consultant's favorite answer, which is it depends, because it always depends on your sample size, on your demographics, everything. But I believe folks here are have some familiarity with statistics, so I don't need to harp on about that. So let's jump right into things. We're going to talk about, well, actually, before we jump into things, I just want to say that if there are questions throughout this session, feel free to ask them in the chat. Feel free to raise your hand. I will try to pause on a regular basis just to give room for this content to breathe. Our next scheduled break will be at 3 o'clock. I am going to move through the code at a somewhat brisk pace. Again, I will be posting the code after this session is done. It will be available on GitHub along with any of the data files you need. So feel free to sit back, relax, follow along, and enjoy the ride. All right. With that disclaimer out of the way, let's talk about logistic regression. So the first machine learning algorithms that we're going to be looking at is we're going to be looking at doing logistic regression. So we're going to be doing some supervised machine learning. So we have been, let me set the scenario for you. We have been supplied with data representing 125 individuals. Inside of this data file, we have information about the age, gender, blood pressure, status, cholesterol level, whether the person has a fever, whether the person has a cough, and whether they have a particular disease or not. So we have been asked to construct a model that will predict, given a new individual's statistics like this, whether that person has a disease or not. And we're going to do this by first building a logistic regression model. Now, what is a logistic regression model? Well, this is a type of linear model that will help us estimate the probability of an outcome happening. And this outcome in this case is a binary outcome. Yes or no, true or false, sick or not sick, will default on loan, won't default on loan, success, failure. So this is different from a linear regression model. So in a linear regression model, our predicted values, they can take on any range of value, right? So we can get any range of value out of a linear model. Logistic is going to produce a binary outcome, 0 or 1, true or false, that we can then find a probability for. So when we ask our model to, when we ask the algorithm to predict the outcome of our model or the outcome, we can also ask, what is the probability of this outcome? We'll also be able to train our model and see how often do we expect false positives, false negatives, true positives to occur. We'll get into that in a few minutes. So the data file that we'll be looking at, if you're following along, and I posted the GitHub link earlier today. I'll post it again in the chat just in case anybody missed it. But the data file that we'll be looking at is demo1labeled.csv. And this demo file, believe it or not, is generated by ChatGPT. Yes, you can ask if ChatGPT has reared its head once again. You're probably tired of hearing about it at this point, but hey, it is an interesting technology. I found it's fantastic for generating fictional data, especially data that we need to use for demonstration purposes. So this is not identifying any particular person in the real world. Any relationship to any person's living or otherwise is purely coincidental. So this file contains 125 participant records. And again, it has their health status. So let's take a quick peek at this file. I'm going to open this file up in Excel. Again, this is demo1labeled.csv. So if we take a look at this data file, we see that we have a column for age, gender, blood pressure, which looks like a categorical variable, cholesterol level, whether they have a fever, whether they have a cough, and a 0 or 1 to represent whether or not this person has a particular disease. Again, this data is all fictional. So this is the data that we're going to be feeding into our algorithm, into a logistic regression model, and try to make predictions. So the goal of our machine learning model is we want to be able to have our machine generate a prediction given a new set of these attributes. For example, let's say we had somebody that was 38, male, with normal blood pressure and cholesterol level around 130 without fever and cough. What's the probability that they have a disease? First off, does a computer think that they have a disease? And if so, what is the probability? So this is the data set that we're using. Let's talk about the environment in which we will be conducting our analysis. We will be using Python, and in this case, I'll be using the Spyder editor. And this comes from, this is installed from the Anaconda Studio package. I'm a big fan of the Anaconda Studio package because it just bundles everything that you need into one easy-to-use package. If you've got PyCharm or some alternative editor available, feel free to use it. It should work there. The DABI 2 course that I teach, we make heavy use of Spyder and Anaconda. I like it. It's a fantastic way to get started. In the previous session, Anado was using R. And during the office hours chat, we were talking about, should we use R, should we use Python, which is used more in the realm of data science? And my favorite answer to give to that question is yes. Both are used. Both have their strengths. R's primary strength is in statistical analysis. Python is more of a general purpose programming language. You can make full-blown apps using Python, and many people do. In my own consulting practice, what I've seen is Python is used to do the heavy lifting of data cleaning. So we use Python to prepare our data files and then ship those off to statisticians who are more familiar with R for doing, say, their linear regression analysis. So Python has a ton of applications in data science. There are packages available for doing linear regressions, for doing machine learning, for doing visualization. And I find that it has a fairly simple, easy to learn language syntax. So the actual lines of code that you're going to write compared to other languages. I find it's less intimidating than some other languages. What you will find is that if you decide to take a further look at Python and R, you'll find that their syntaxes are quite similar. In fact, in one of the courses that I teach, our section on R is just a review of what we did in Python just using R. In general, what I found, though, is statisticians love using R. The computer science folks and the people that are doing the heavy lifting of preparing data, we love using Python. But both have their place. And one last sidebar that I should mention about Python, and another related question that I do get is, I've heard of Python, I've heard of R, and I've heard of SQL. Which of the three should I learn? And again, my answer is yes, you should learn all three. SQL can be a fantastic language to learn. I know that there are, that with National Research, my work with National Research Council, they're sitting on a ton of SQL databases, and very often they will, I'll write SQL queries in my consulting work for them that they will ingest into Python or R. So you can use SQL as a language within Python and R to read in data and do your data transformation. So if you know those three languages, you've got some pretty powerful tools in your data science toolkit. So that's my recommendation. I would explore all three. All right, let's hop in and talk about our environment and where we'll be doing our analysis work. And that is going to be in the Spyder programming environment. So inside of Spyder, we're going to be taking a look at three main components. First is the code editor. So if you open up Spyder on your computer, the code editor is usually the pane on the left. This is where we're going to be editing our Python code. So it's just like your web browser. You can have multiple files, multiple tabs open at once. And just above the tab is where your working directory is displayed. And this working directory is going to be important. What I like to do is make sure that my Python files are saved in the same folder that my data files are saved in. The working directory is what Python uses to find your data files, like your CSV files. So if you're ever running a Python file or an R file and you get a file not found error, check to make sure you got the file name spelled correctly, and then check to make sure that your working directory is the same folder as where your data files are stored. Down in the lower right is our output console. So anytime we use a function such as print, we can see the output show up down here in the lower right. One other sidebar about Spyder is when we start up Spyder for the first time, it will create a new Python file and kind of place it in the middle of nowhere. My recommendation is always do file save as, save your Python file to the same folder as your CSV files. That way you'll know that they're saved beside each other and you won't have to worry about the working directory stuff. We do have a question, which is, can you explain what is Python and what is Spyder? Absolutely. So Spyder is the editor that we're going to use to write and run our Python code. So Spyder is to Python like RStudio is to the R programming language. So in the morning session, Anado took us through programming in R, and he was using RStudio to do it. When we're programming for this session, when we're programming in Python, we're going to use Spyder to write our code and to run our code. And then Python is the actual language that we will be using to give the computer instructions as to what we want it to do. So R is a language that so R and Python are both programming languages. They're what they sound like. They are the instructions where we tell the computer what we want, what we wish for it to do. And just like English and French have different syntax, they perform the same thing. They convey some sort of meaning to another human being. R and Python are like that, and they are different ways to convey meaning to the computer, to tell it, here's what I want you to do. Does that address the question? Great. Good. All right. So in order to read in our files into Python, we need to, or in order to work with our data in Python, we need to read in our data from CSV. R has a function for this built in. It's read.csv. We have to bring in a bolt-on library into Python in order to read in our data. And that's where the Pandas data analysis library comes in. So because Python is a general purpose programming language, we need to bring in these libraries. Think of them as Lego pieces that we can bolt into Python to expand what it can do. So we're going to be using Pandas to read in our CSV files into the computer's memory and then do some sort of manipulation with it. So with that, we're going to write some code and read in our first data frame. So here we go. First thing I'm going to do is import the Pandas library. I'll type in import pandas as PD, and then I'm going to read in my data into a variable called data. All a variable is a named spot in memory where we can hold some data. In this case, I'm creating a variable called data, and I'm going to say, hold the result of reading in a CSV file from my computer's hard disk. So I'm going to say pd.readcsv and then put in quotes the name of my file, which is data1 or demo1 underscore labeled.csv. And if I run this code in Spyder, on Windows, I can use F5. On Mac, I believe it's Command R, but I cannot remember the keyboard shortcut at the moment. You can also go up to the run menu and hit run menu, run, or hit the big green play button. If I hit F5, run this code, you'll notice up here, I have another pane called the Variable Explorer. And I've got one variable up here. It's called data. It's a type data frame. And I should step back and explain what a data frame is. And all a data frame is a structured table-like format to hold data in Python. We have columns and rows of data. And in Python, we can build our data frames two ways. You can do it manually by actually manually typing in the rows and columns in your code, or we can use functions to read in those files from our computer's hard disk. Pandas also has functions to read in from Excel, and I believe it has a function for reading from SQL as well. Yes, it does. I doubt we'll have time to take a look at that, but if we do, I can always pull up a quick demo, I'm sure. So we have one variable up here called data. It's of type data frame. Now the size, what does the size mean? 125,7. This tells us we have 125 rows and 7 columns of data. If I double click on the name of my variable in my Variable Explorer, this new Data Frame Explorer will pop up. And I can preview what's inside of my data frame and get it and just see at a glance, what kind of data am I dealing with here? So I can see I've got a column called age. You'll notice the age column is highlighted. And that is Panda's way of telling us this column contains numbers. And this highlighting is showing the range of minimum and maximum values in my data. My gender column, it looks like it contains text. Same with blood pressure. Cholesterol level also, it has been read as a number. Fever and cough, we've got text. And then has disease has been read in as a number, either a 0 or a 1. Question in the chat, is the demo 1 from a default folder location that Python reads automatically if no folder location is written out? Great question. So where are we, if I translate that question, ask that question another way, the question sounds like, where are we reading this file from, this demo1 label.csv? Is that an accurate way of rephrasing? Awesome. So I mentioned a moment ago about the idea of the working directory. if we don't specify an exact file path, so for example, I'm on Windows, so I could say something like "see my source demo1 labeled." And I could say, here's exactly where to find this file. In this case, I'm saying, I want you to read in this file, demo1 labeled. Python by default is going to look for this file in the same folder that your Python file is stored in. So if your Python code file is stored in the same folder as your data file, then Spyder and Python are going to find that data file. So that's why I like to save my Python code files in the same folder as my data files, because that's where Python is going to look for my data files. So for example, on my computer, I have stored this under source ps627_hc. I have my demo Python file here, and then I have my demo1 labeled Python or data file here. Does that address the question? If we don't specify a folder location, where Python is going to look for your data file in the same folder your Python file is saved in. Awesome. Cool. Great question. All right, so we've learned how to read in a data file and explore it in our data frame explorer. Now, something else that we could do is we could get some summary statistics about this data frame. For example, we could print out to our console data.describe, and we can get a little bit of details about our data frame. For example, for our numeric columns here, I see for age, I have 125 rows. The mean age is 44.5. And my minimum age is 23, and my max age is 70, and I see my different percentiles. Cholesterol levels, I get the same statistics. Has disease, I get about the same statistics. And interesting that our mean is 0.6, which means our data seems to skew towards having disease rather than not having disease. So interesting. I hadn't actually looked at that summary statistic until just now. So kind of fun to take a look at. All right,
Elias. This is Anand though. I'm sorry,
yes,
but it's like I just see the slide still. I don't see the output you're referring to.
You see the slide still, not the output.
Correct.
Can others also confirm in the chat? Do you see do you see Spyder, or do you currently see the slides?
I'm seeing Spyder.
Okay, I'm getting a few folks in the chat saying we see Spyder. The consensus seems to be Spyder. It might be. Yeah, it looks like the consensus is Spyder. So
I would suggest continuing.
Yeah, I'm gonna continue on the assumption that we're okay. Thank you though. Okay, a question that just came through the chat. I can see Spyder, but also wondering how to comment in Python like R or Stata. Awesome. So in Python, we use what used to be called the number sign, but in recent years, we've referred to this as the hashtag. Ask anybody that is in Gen Z what that is, and they will say it's a hashtag. We use we use number sign to write comments. So for example, I can put a comment here that says, write out summary stats for our data frame. Used to call it the pound sign. Yes, once upon a time it was pound sign. Ah, good times of calling cards. Anyway, before I date myself any further, we'll keep moving along here. So we've described our data a little bit. Now notice that we didn't get summary statistics for any of our other columns, for our non-numeric columns. Now it is possible for us to get some summary statistics for those columns. And what I'm able to do actually as well is sometimes in Spyder, I'm able to actually get help for a particular function in Spyder. It doesn't appear to be working with me today. But you can always go to the handy dandy documentation, right? So yeah, of course, the demo doesn't work whenever you're live, right? Of course not. So what we can do is, I've only gotten, by default, if I use describe, I will get the summary statistics for only numeric columns. If I want to get summary statistics for all of my columns, I can say include equals all. And what I'll get for my non-numeric columns is the top occurring items, the number of times that top item occurs, the number of unique items appearing in that column, etc. And apparently the screen seems frozen. So I'm going to stop share and restart share and see if that helps. Give me 1 second here. All right. So I've restarted the screen share. I just want to confirm that we're going okay. I'll take this moment to actually answer another question. So can I load up a messy data frame that is not easily machine readable, such as an Excel spreadsheet with merged cells, empty rows, and columns, and rows containing unlabeled data that is labeled somewhere else in the data frame? That's a fantastic question. So can I load up a messy data frame that's not easily machine readable? So this would be, I could see a couple of steps for doing that. I find that Python, that Pandas read Excel is good for more basic scenarios where your data is already somewhat close or at least in a table-like format. So for example, if you've got an Excel file where you've got some tables in it already, I find that Pandas can ingest that data quite well. What I would suggest in a case like that, where you've got, say, what you would maybe refer to as a messy Excel spreadsheet, is you might want to do some form of a pre-transformation. For example, you might need to do a bit of manual cleaning on that file to transform it into something that would be a bit more easily machine readable. Or if, for example, another approach that you might take is there are libraries for other languages like C#. In fact, this is something I've done in quite a few occasions, where we've been given an Excel file and we need to do some preliminary data cleaning on that so we can bring it into, say, Python or into a database. Well, actually, there's a library in C# called EP+ that we can use to read in that Excel file, do our manipulation, transform that into more of a table-like format, and then prepare it for something that we could then read into Pandas and read into Python. Could you do it with Python? You might be able to. Depends. I've not tried Python. I've not tried Pandas with calculated columns in Excel. So my answer would be, there's probably a way to do this that isn't too hard. The caveat I would put is that you need to have, what I find is when you're transforming, say, a messy data file, is there needs to be some sort of a set of instructions that the computer can follow to transform your data. So for example, if your data is spread out across a bunch, like if you're having to do a bunch of, I'm just trying to think of a good example. I don't have one at the top of my head, but there needs to be some sort of a way that you can map when you're going to be doing work in Pandas, you're going to need some sort of a table-like data format. And so there needs to be you need to be able to come up with some sort of a mapping of your current data into a table-like format. And so whether that is doable in Python or whether that's doable in another language like C#, as long as a process like that exists, then it would be possible to do that. I don't think we'll have time to take a look at a specific example, but I would say it's possible, yes. Further comment in the chat is merge cells. I'm not sure, but empty rows columns worked. Unlabeled, it just assigns a default ID. It's just a bit harder to change names sometimes, but it can be done. I mean, yeah, you can do any kind of transformation. Again, it just depends on what state the data is in. That said, as well, if the data is, if say you've got different sheets and your data is already in tables, then for sure you could ingest those tables into Python, do your data transformation, and then on the other end, spit out, use Python to say generate a CSV file or an Excel file. I believe Python, I believe Pandas can generate Pandas can definitely generate a CSV file, and it looks like it can also generate. It looks like it can also generate Excel files, so that's an option as well. Quick explanation. Can you explain what the first line import pandas as PD does? Yes. So pandas is a library that we use. It's a extra functions that allow us to read CSV files into Python. Python can't read in CSV files on its own, so we need to bring in an extra library. The as PD allows us to, instead of writing pandas dot anytime we want to use something from pandas, it allows us to alias this pandas library so that I can just type PD dot instead of pandas dot. So without this as PD, I'd have to type pandas dot read CSV anytime I wanted to use functions from the pandas library. Another question is, you do not need to call in libraries first like in R. So the R equivalent, let's assume like pandas existed for R, right? It doesn't, but let's assume it did. The R equivalent of this first line would be library pandas. So great analog. Library pandas, so the R equivalent of import pandas, approximately, would be library bracket pandas. Yeah. So that is a difference in how we, so notice that how the languages differ a little bit, where instead of saying library and then the library name, we write in import and then whatever library we want to import. So yeah, great catch. But yeah, I'm going to use the as PD. So I'm still getting folks saying that they're seeing a blank screen, but just again, a quick tech check. Everybody is, I don't know, maybe give me a thumbs. Yeah, all good, fine for me, looks good for me. Okay. I'm going to proceed on an assumption that things are okay. We're also recording the session, so if there are issues, our apologies. But we're gonna move on. We got a few items to still cover. Okay. Alrighty. So we've read in our data. I'm gonna speed up just a little bit because I want to get through a little bit more content here. Now that we've got our data into Python, we want to build up a logistic regression model. And again, reminder, logistic regression, we're trying to get a yes or no answer out of the machine. And we're going to build up our regression model in 5 steps. We've already done step 1, which is read in our data. Step 2, we have to prepare the data. So we have to, if there are any columns that are not in a numeric-like format, we need to transform them. If we have, then we split our data into testing and training sets. What do I mean by testing and training sets? Well, in order to build a model, we have to give it a certain amount of data to actually build a model around to make our predictions. Then, after we've trained our model, we want to see how well does it predict given already known data. And so that's our testing data set, where we'll say, okay, here's some data, make predictions, and let's see how accurate those predictions are. Then we train our model by feeding in the training data, and then we test our model by feeding in the test data. After that's all built, we evaluate how well does the model do our predictions, and then we can start feeding in new unlabeled data. So how are we going to do this? Well, we have to bring in another library. In this case, we're going to bring in the scikit-learn library. And I'm going to use a slightly different import format. And I'm going to say, I'm going to bring in from scikit-learn, just checking, just doing a quick check here. So I'm going to bring in two functions from the scikit-learn library. I'm going to bring in the logistic regression function. So this is what we use to build up our logistic regression model. And then I'm also going to bring in a function that allows me to split up my data into testing data set and training data set. All right, so I'm going to bring in those two libraries. Next, what I'm going to do is I want to create a subset of my data. And this subset is only going to contain my age column and the cholesterol level column. So we're going to build a basic model first that tries to predict disease based on age and the person's cholesterol level. So we're going to ignore all the other attributes. In the next demo, we'll include them. But for now, we're going to just build a model using our numeric variables, age and cholesterol level. So I'm going to create a new variable called data subset. And I'm going to set this equal to data. And I'm going to filter data by giving it a list of columns that I want to keep, which is my age column and my cholesterol level column. Now, if I run this code, you'll see now that I have two variables in my data frame, in my variable explorer. I have my original data frame, and now I have my data subset data frame, which only has age and cholesterol level. I've stripped off the labels as well, and that's going to be critical. We don't want to include the labels in our model yet. If we include the data, if we include the labels as part of this data frame that we're going to be feeding in, then those labels are going to be treated as another input variable and not the labels. So we're going to be able to feed in the labels separately. Next, this is where we split up our data. So I'm going to be declaring 4 variables at once. I'm going to create a variable called training data, a variable called testing data, a variable called training labels, and a variable called test labels. Now this line is getting long, so I'm going to say that this is equal to, and I'll use the backslash to say to Python, the next line, treat it as part of the current line that I'm on. So I'm going to say test labels equals train test split. The first parameter I'm going to pass into train test split is my data subset. So I'm saying take my subset of data, age and cholesterol level, and split this into 2 groups, training and test data. The next parameter I need to pass in are my labels. So you can think of data subset as my X and my labels as my Y. And I'm going to say my labels are my has disease column. So my has disease from my original data frame. Then I'm going to say test size. I'm going to set this equal to 0.5 or 50% of the data. So split the data into 2 groups using putting half of the data in one group, putting half of the data in the other group. First half contains my test data, second half contains my training data. If I run this code, I now have a bunch of new variables that show up in my variable explorer. I have one here called test data. And this is the data that I'm going to be, that after we build up our model, we're going to test to see how accurate is this model. So this is the data we're going to compare against when we test our model to see how well does it make predictions. Then I have training data. So these are the individual rows that we're going to use. These are the individual rows that we're going to use to build our models so that we can make our predictions. Question in the chat, which is, if I'm receiving a module not found error for sklearn, that would that suggest it's not installed? That is correct. If you are receiving a module not found error, then you likely need to install the scikit-learn library. And if you're using a package manager like pip, you would do pip install sklearn, and I'm pretty sure you can just do that in your Python console. So we do pip install sklearn. So I'll paste that into the reply there. I don't want to do this on this system right now. All right, so we split up our data, and you may have noticed as well that we have this exclamation mark, this warning next to sklearn linear model import logistic regression. Spyder is telling us that, hey, you've imported this function, but you're not using it. So far, we've just split up our data into test data and training data. Now, we're going to build our model. And we're going to build our model by creating a new variable called model. I will set this equal to logistic regression, open bracket, close bracket. We've now created our logistic regression model. We're ready to train it. So all we've done so far is created a blank, empty, untrained logistic regression model and split our data into test data and training data. Now we're ready to train. So we're going to say model. We're going to say model dot fit. And we're going to pass in our training data and our training labels. And with that, we now have a logistic regression model. That's it. We have built a logistic regression model in Pandas, in Python, excuse me. Now the next reaction is, so what? We haven't made any predictions with it yet. Well, remember what I said earlier, which is we read in our data, we prepare our data, we split the data into testing and training sets, and we train our model. We've done those 4 steps up to here. So this trains our model. I'm going to give myself a few more lines here. Now it's time to test the accuracy of our model. And so what we're going to do is say test prediction labels. I'm going to create a new variable called test prediction labels. I will set this equal to model.predict, and I'm going to feed in our test data. I have a new variable now called test prediction labels. What has happened is I have fed in our test data set, which is this data frame here. Which is this data here. And now our logistic regression model has attempted to classify whether each of these rows has disease or does not have disease. So first data frame on the very left-hand side here, this is our test data. Here's our prediction labels. Let's take a look at the actual labels and just see if we can eyeball how well our machine learning algorithm did. So our first row has disease is 1. The actual label is 1. The predicted is 1. So it got it. Second row, predicted was 0. Actual was 0. Third, predicted was 1. Actual was 1. Continues all the way until our 6th record, which is predicted was 0, but actual is 1. We got a false negative. And then the next 2 rows, we predicted 1 has disease. For the next 2 rows, the actual was 0. We got 2 false positives. Interesting, right? Now, eyeballing it is one thing, and that kind of sucks to eyeball it. And I see there's a question in the chat. I'm about to get to it. Eyeballing sucks. Is there a way that we can compute the accuracy? Yes, there is. If you just heard that in the background, my child just threw me a brand new library and function that we're going to bring in called accuracy score, which also comes from scikit-learn. So I'm going to come back up to the top of my file and say from scikit-learn.metrics import accuracy score. And this is going to allow us to quickly determine the accuracy of our logistic model. So the question in the chat before we determine the accuracy is, do we need to specify the dependent and independent variables? So in this case, we sort of have, because we've split up my data subset here. These are my independent variables, my age and cholesterol level. And then my labels are my dependent variable, what we are trying to predict. So that's our, anytime I'm referring to labels, yeah, we're referring to our dependent variable. All right. Let us see how accurate our model was by saying model accuracy equals accuracy score. And we're going to compare our test labels versus our test prediction. This line's getting long. Our test prediction labels, and we will print out model accuracy. And if we run this code, the result we get is that 84% of the time, our model predicted correct. Our model got a prediction that matched the actual, 84% of the time. I'm going to perform a magic trick. You ready? I want you to keep an eye. So the prediction, the accuracy we just got was 84.1%. Okay, keep your eyes locked. Watch this. Do you see what just happened down there? I ran this code again. Did you notice that our accuracy changed and now all of a sudden it's 80.9%? Watch this. I'm going to run the code again. This time it's 88.8%. I'm going to run it again. This time it's 77%. What is going on? You're probably wondering. Or you're going, man, that is a lame trick. There's no trick going on. So what happens is every time we run this code, when we run train test split, train test split will split up our data set into test data and training data randomly. So the way it splits up the data is dependent on the random number that Python generates in the background every time we run this code. That's what the consequence of this is. Every time I run this model, I get a different, or every time I run this code, I get a different model. My model is trained with a different subset of the data. So I get different predictive models. My accuracy changes with each run. Now, let's say I wanted to get the same randomness every time. I could say after test size, I could put a comma and say random state equals, let's say, 42. Now, what is that going to do? It's going to do what's called setting the random seed. And the long and short of it is it says, generate your random number and use this as your base number. So the computer's going to do a bunch of algorithmic magic in the background, and it's going to come up with a random number. But because I'm saying use this known value, we're going to get the same random number every single time we run. So now if I run after specifying random state, notice the accuracy is exact same every single time. That is because we're splitting the data set up exactly the same each run. Now, if I change this random state from 42 to 43, whoa, look at that. I get a completely different model. My model accuracy goes to 80%. I can say random state equals 44. Well, 80%. Let's put it to 46. Let's put it to 49. Let's put it to 23. Hey, not bad accuracy, 87. So I've got a model that makes the correct predictions 87% of the time. Now, how can I gauge the rate at which we're getting false negatives, false positives, true negatives, and true positives? I could do that by using something called the confusion matrix. So using the confusion matrix. So what is a confusion matrix first? Confusion matrix is a way to get from the model how often will we get given a prediction, how often should we expect to get a false negative, how often should we expect to get a false positive, how often should we expect to get a true negative, so 0 and the answer is 0, and how often should we expect to get a true positive. So I'm going to come back to top of my file, from scikit-learn.metrics, import confusion matrix, and I'm going to create a confusion matrix by saying cm equals confusion underscore matrix, and I'll use my test labels, and I'll compare this to my test prediction labels. So I'll have a new variable in my variable explorer called cm. Now I get this table-like format. So what is going on here? So the top left corner represents our true positives. So 18 of the test cases, we got, if we compare our test cases to our actual, we get 18 true positives. We get 4 false positives. We get 4 false negatives, and we get 37 true negatives. Now we can turn that into a probability by doing a little bit of maths. So we could say CM percentage equals our confusion matrix divided by each value in our confusion matrix divided by the sum or the total of all or the number of data points we have in our confusion matrix. And now we can see 28% of the time we got a true positive, 58% of the time we predicted true negative, 6% of the time we got a false negative, and 6% of the time we got false positive. Now for the fun bit, we're going to predict a value. We're going to predict a value. So just for funsies, let's go back to our original data here. And I'm going to grab this record, this row. So a male, 55 with a cholesterol level of 180. So I'm going to say predicted data equals, in brackets, 55, 180. Now, before I do this, I want to address an awesome question. Is the variation in accuracy between runs because each run has selected different splits for the test data and the training data? Yes, 100% that. If I don't specify my random state in train test split, each run will have those data sets split up in different ways. So that will account for the differences in accuracy. If I specify random state, I will be guaranteed for each run that the data will be split up the same way. Now, each of the random states that I specify, which is a number, will be split in different ways. So the way that random state 2022 is split up may be different from random state 2023. But if I specify random state, I can guarantee that the way the data frames are split is the same with each run. So what I'm doing here is controlling for the randomness. What percentage, another great question, what percentage of data should typically be used as training data and as test data? Oh, good question. It's up for interpretation. Some folks will use 20% of the test data. Some folks will use 50%. It depends how much data you have. In general, the more data you use, the more you could run the risk of overfitting your model. In this case, because we only have 125 rows, I want to err on the side of maybe overfitting a little bit more than underfitting because we don't have a lot of data. If you had thousands of rows, then I would say using a subset of that, like say 20%, would be good. It's a rule of thumb, and it depends. Another question is, can the seed be set globally, or is it just within the function? So the only place where the randomness shows up is in this function. So the only place where any randomness in this process shows up is in this train test split function. And by the way, this train test split is a convenience function for us so that you're not manually splitting the data into two different testing and training data sets. You could do this process manually. We're not, because the first principle of computer science is that if we can get the computer to do it for us, we get the computer to do it for us. So this is the only, so this train test split is our only source of randomness in the entire, in our entire process. Now, could we control the entire random seed for all of Python? I don't have the answer to that. I'm not sure. But for our purposes, yes, we can control randomness by saying random state equals, and then we provide a number. Okay, let's make a prediction. Let's make a prediction. So we're going to predict the following data. We're going to try and predict, does this person have disease by their age and their cholesterol level, 55, 180. And if we recall that I'm sourcing this from our 12th row in our data frame, which is 55, 180. So this is actual data. In fact, let me get the known good label here, which is yes, has disease. So we expect, so the actual is 1. So we are expecting, if our model is accurate, we should get a 1 here. We should be predicted that this person has a disease. So let's do the prediction. So we'll say test predict equals our model dot predict, and we have to pass it a list of data points to predict, a list of rows to predict. So I'm going to create square brackets inside here to say I'm creating a list of data. This list of data contains one data point to predict, which is our predicted data. And then I will print out test predict to the console so we can take a look at what we get. All right. So with the random seed set to 2023, so we're controlling for our randomness, our model is predicting that a person with an age of 55 and a cholesterol level of 180 is predicting that person has disease. Now that's one thing. What's the accuracy? Let's predict the probability. So I'm going to say model.predict underscore proba, and then we'll print out that probability to the console. So our probability with our model, the probability that this person has a disease, our model is predicting there is a 63% chance, given an age of 55 and a cholesterol level of 180. Let's change this. Let's set this to, say, 32 and 123. I don't know if that's good cholesterol. I should probably go to my doctor. In this run, for this piece of data, for 32, 123, we get a result that says 0 does not have disease. And our model has a 99.7, 99.8% probability that they do not have disease. Let's see, what else can we predict here? How cool is that, though? So we can actually, so we built, so does it give 1 for probability greater than 0.5? So if the probability, you'll see here, I get my probabilities in square brackets. I get my probability of a negative result, negative outcome on the left-hand side, and the probability of a positive outcome on the right-hand side. So in this case, because my left-hand side probability is greater than 0.5, is 0.5 or greater, is going to say, yep, this is I'm predicting that this is a 0. So if I say 40 and 180, look at this. For age of 40 with a cholesterol level of 180, look at the probabilities. It's predicting 0, but it's only predicting it with a probability of 58%. And if I increase the cholesterol level to 185, now it's saying, hey, this person has disease, but I've only got a 53% chance of it. And if I put age of 40 and cholesterol level of 183, look at that. We're pretty much right in the middle. Could go either way, but the probability of not having disease is just slightly greater. So our model is not bad. Our model is not bad. And again, we've got that confusion matrix percentage, and our false positive and false negatives, 5% of the time, not bad. I don't know about you, but I'd go to Vegas with those odds. So let's recap what we've done here. In one of the runs that we do of this model, I prepared the slides based on a different random seed. I'm sorry. So just to recap, let's if we use a certain random seed using just cholesterol and age, we get false negative, false positive about 5% of the time. So if we predict somebody with an age of 45 and a cholesterol level of 190 for a given model, we can predict 73% probability. But if we look at existing data, somebody who's 55 with cholesterol 160, sometimes you might get yes, sometimes you might get no. Let me show you that. So I'm going to come up here and remove this random state. All right, I'm going to remove the random state, and we're going to run these predictions a couple of times. So now that I've removed random state, we're going to split up our test data and our training data into different data sets each time. And we're going to try to predict somebody who's 40 with a cholesterol level of 183. What's the probability that they have disease or not? So this run, I get 56% chance they don't have disease. Another run, 57% chance. Another run, 59% chance they do have disease. We have flipped to yes. So notice again, it depends. The test data. The test data that you feed to your model is important as well. Again, if we fed all of our data into the model, we could run the risk of, say, just overfitting. But if we don't give it enough data, well, we might not have enough data to make generalized conclusions. But depending on the data that we feed in to train our model, we can see different outcomes. So that is a very quick crash course on logistic regression models. So these results, question from the chat, these results are based on one model output. Could you optimize the results based on a different number of model outputs that might improve predictions? So if I rephrase the question, and then let me know if this is accurate, could we make a couple of more predictions and then feed that back into our model as further training data? So in other words, say we had 10 new predictions. Now here's the critical part. Say we had 10 new data points come in, and we have labels for those. We could add those into our training data set. One of the issues with this, so the type of model that we're building here is a supervised machine learning model. A supervised model relies on there being labeled data. So say you have 10 new data points come in. They must be labeled in order for us to use them as training data in our model. If we do not have labels for that, we can't do anything with that data except get predictions until we get actual labels. So let's say we got 10 new participants and we knew their age and cholesterol level. We could make predictions, but that's all we've got. We've only got predictions as to, do we think they have disease? Do we not think they have disease? It would then take somebody to go into the field and say, okay, right, participant 1, do they have disease? Yes or no? Yes? Okay, cool. Let's compare that to the machine learning model. Maybe we feed that in as further training data. Does that address the question? So could we optimize results? So we can give feedback via reinforcement. So we could feed that, again, we could say, let's increase the amount of tests. The first quick and dirty way is just to say, let's do the test size is say 75%. So we say, let's use 75% of the data, run this, and then let's see how that affects our model's accuracy. And with a couple of runs, I see accuracy kind of hovering around the 80% mark. So, is that better than, say, a 50% split? Not entirely. So, again, this depends. You could, if you have data, like one where it might be helpful is, say you do notice that that the model gets a lot of predictions wrong. You could feed that back into the test data or into the training data, train them, refine the model further, and then you might come up with better outcomes. Every time we see a warning, how should we interpret the results pane? So this warning is just letting us know that I'm actually, let me see here. Where's that warning coming from? So this warning is coming from the fact that in my logistic, when I'm creating my logistic regression model, I'm not providing actual labels. For example, like has disease, does not have disease. This is a warning that we don't need to worry about. So it's just warning us that, hey, if you're expecting to get more than just a 0 or 1, you're missing something. Does the function which splits the data set maintain the same event rate of disease in both the training and test data sets? In other words, does it make sure that we have the same proportion of like has disease, does not have disease? Like, for example, we're splitting the data set into 2 groups, size 50%. So in our training data, we have 62 rows, and in our test data, we have 63 rows. Are you asking if it makes sure that our test data, our training data has, say, 31 rows of has disease and 31 rows of doesn't have disease?
Hi, this is Anata speaking. I just wanted to say, like, if there is a 10% event rate of disease in the overall data set, is that maintained in both of the data sets? Like, does it sample without replacement or?
Okay, so I see. So like, does it maintain that proportion? So the way that train test split works is it is possible, depending on how the data set is split up, because it splits it up randomly. It doesn't do any proportions. So it's possible that, say you had a 10% has disease rate, and then 90% of your data does not have disease. It's possible for all of the disease data to end up in your training data. So you could have like training data that skews one way or the other. The idea behind train test split is we're saying, if we say let's use half the data, we are making an assumption that our data is more or less not skewed. Now, are there ways where we could say, now again, train test split is splitting the data up for us. We could go through and split the data manually. And this is beyond what we're going to do in this workshop, but you could go through and split the data manually so that you maintain that proportion, that 10% proportion and 90% proportion in your training data. So you could go through and do that manually. So we are making an assumption here that that we're not heavily skewed one way or the other. Is it a problem to always use the same seed across many research projects? Should researchers do anything to account for different results from different seeds? I don't think I can't see. So the idea behind the random seed is basically each time, imagine when in train test split, what we're doing is we're going to split our data into 2 data sets, and we're saying take 50% of the data, put it in the training data, take 50% of the data, put it in the test data. So we're going to roll a dice. So we got 125 rows. We're going to roll a dice 125 times, once for each row. What that random seed is, it controls for the random numbers that are going to be generated for each dice throw. So in other words, we're going to get this. So for this data set, if we specify a random seed, we're always going to split this data set the same way each time. that's not going to have if you're splitting up another data set, it's not going to have controlling the same random seed is not going to guarantee that you split things up and get the same kind of dice rolls on the other machine. It's just a method, so you shouldn't need to worry too much about using same or different random seeds across different research projects. Can you explain why the above process was called machine learning? What did the machine actually learn? Okay, fantastic. So this gets to the heart of what we're doing here today. What the heck? So I'm saying this is machine learning. So what we're doing here is we have created, instead of writing code that says, if the age is great, like our traditional prediction, say we were doing this in a traditional programming model. I'll create a brand new data file. I'll say age equals 40 and cholesterol equals 128. So we could, in a traditional model, in traditional programming model, we do something like this. If age is greater than like 45, we would then go in, say, and do some other check and say, like, if age is greater than 55 and if cholesterol is greater than 120, and I'll create a new variable called has disease, and I'll set that equal to false by default. Has disease equals true. And then I as a programmer would then need to go and write all of the other rules for, I'd need to go and write all of the other rules to handle all the other cases. So like else if cholesterol, or for example, else has disease is false, blah, blah, blah. And I'd have to go on and implement this an algorithm to say, given an input of age and given an input of cholesterol, run through these rules and spit out yes or no. What we're doing in this demonstration by building a logistic regression model is we're saying to the computer, take a look at this data. Take a look at this training data and then try to build an algorithm in memory that when you're given a age and a cholesterol, you can figure out, you can make a prediction of whether that person has a disease or whether they don't have disease. So that's why we refer to this as a machine learning algorithm. Now, here's where the learning bit comes in. So say we make 10 or 20 or 30 more predictions and the algorithm gets, out of the 30 predictions new predictions we make, it gets 10 of them wrong. We could then say, okay, let's take this new set of 30 predictions, give it the correct labels, feed that, add that into our tests, into our training data, retrain the model and refine the model so that we can say, here's the items that you classified wrong. Here are the actual classifications in an attempt to improve future predictions. That's where we get into the true machine learning. Does that address the question in sufficient detail? So really we kind of broken this into two steps. One is we're creating the algorithm from our existing data, and two, where we get into the real machine learning would be where we take data where the computer has gotten it wrong, feed it back into our training data set in an attempt to refine our model to get a more accurate model. Another question, could you loop this code with different random seeds to generate 100 different models and then identify the model that produced the most accurate result? For example, the best of 100 models in terms of overall accuracy. Yeah, that is a way that you could do it. And in fact, in another related example to that is if you're doing k-means clustering, one of the classic problems there is how many clusters do you want to create? And one of the ways that you can do that is you can, I forget the metric we're looking for. There's a metric that you can look at, and what you basically do is you basically create, you do one run with 2 clusters, one run with 3 clusters, and you keep doing that until you find the point of diminishing returns. And then you say, okay, the ideal number of clusters based on point of diminishing returns is like, it's 5 clusters. So we're going to create a model with 5 clusters. That's our optimal number. So you could loop this code with, say, 100 different models, 1,000 different models, and then take the model that has sort of the best overall accuracy and use that. Nothing's stopping you. So how do we apply the model with the highest accuracy so far? Okay, that's a good question. So that's, again, where that's where it might be handy to control for the random seed. So again, that's where we could use random state equals 1, random state equals 2, random state equals 3. There's a bit of trial and error here where you would need to say, okay, let's try different random states, run a couple different models. When we find the random state that works for us, boom, let's lock that in. Now, just being cognizant of time, it is 5 minutes to 3, and I believe at 3 we have a 30-minute break, correct? Yes. So I don't want to launch into another example. I can get the next example started, but I'll pause here to answer a few more questions. How's that sound? So another question, isn't selecting the most accurate model out of a multitude considered cherry picking? It could be. And again, we could be running the risk of like if we say we use all of our test data or all of our data as training data, we could run the risk of way overfitting our model, and we could be cherry picking for sure. So this is where we could get into some interesting discussion about about predictions. So say we get new data and there's, the machine gets things wrong, say 1 out of 3 times. We could provide those corrections to the machine and to our model, and perhaps build up better models later on. So yeah, I guess it could be considered cherry picking, but depends on your intent. I'm going to step back and say that that getting into evaluating whether or not something is good or not good in terms of selecting the most accurate model or any of the maths behind this, that is me starting to get a little bit out of my depth. I'm here to demonstrate. I can demonstrate how to build these models. This is where the hard work begins. It's like, okay, now that we've got these models, what is it telling us? How well does it predict? Are we overfitting? And there are other metrics that we can use. And I'll see if I've got demos on those metrics later on. But this is where we have our results. This is where the hard work begins, where we have to say, okay, well, what does this mean? What do these results mean? Because the computer is only going to give us results based on the input data that we give to it. So say we give it input data where it's skewed, where 10% of the population has disease and 90% of the population doesn't. Well, the model is only going to be so good. And in that case, we're going to have to split up our data. We're going to have to be a bit more intentional about how we split up our data. So the computer can only give us results that are as good as the data, as the inputs that we give to it. So the 2 hardest parts of data, of machine learning and data science in general, in my opinion, are preparing your data and making sure it's clean and ready to go, and then interpreting the results. Great question just came through the chat. Is Python able to handle big data sets, say more than 1 million records? Is there a limit, and would it take a long time to run? So yeah, as the data sets get larger, you're going to start running into some longer run times. In fact, just for funsies, I use the word funsies a lot. Just for funsies, I'm going to read in. I'm going to read in the example where we do the COVID case data. And I fit this. So what I'm doing with this COVID case data, and we'll try to get to this example before the end of the course, or before the end of the webinar. But the idea behind this, and I know you guys want to break because we've been sitting here for an hour and a half listening to me ramble. So TLDR, what we're doing here is this is our COVID case data has like 1 million or more rows. So if I say, here's 100,000 rows for you to chew on, let's see here. So 1, 2, 3. So I'll start timing it. So we're creating 2 clusters in this data set. So far we're up to about 10 seconds to do that on 100,000 records. I know, I need the Jeopardy music or something right now. So it is taking a little bit of time to run on, say, a data. When I'm doing this clustering and I'm using 100,000 records, Python is taking a little while to chew on this. So yes, you can read in large data sets. In fact, if I go up to, once this is done running and I get access to my Variable Explorer again, actually, if I also look at the COVID positive data, I'm just going to take a look and see. So that data file has 1,615 rows. And Python is able to read that into memory no problem. Now, an algorithm like this, if you're of a certain age, you probably remember back in the 90s, you turned on your computer and then you went to go make a cup of coffee, and then 15 minutes later, you'd be able to use your computer. We're kind of at that point today with machine learning with very large data sets where you say have more than, I'm going to say a large data set is anything with, say, more than 10,000 rows. So yeah, we're well into a minute and a little bit. We'll actually let this chew during the break. But yes, Python can handle large data sets. Your biggest limit is most likely going to be your computer's memory. If I take a look at what's being used on this computer right now, what is Python using? Let's see. Oh, looks like it finished running. So that was about, it looks like it was about 2 minutes for it to create k equals 2 clusters for 100,000 records. And our data has 16, yeah, our data has 16 columns. So that's actually, that's a decently sized data set. And Python needed quite a bit of memory for that, but it can be done. It can be done. And a comment that just came through the chat is, I think machine learning in general is a data digging approach, and some people don't like to use it for casual inference. Instead, use it for hypothesis generation process. Yeah, machine learning has got, I'd be careful. So what we'll find after the break, and I know I'm cutting into your coffee time, what you'll find with machine learning, and especially unsupervised machine learning, is exactly that. It allows you to start saying, okay, again, we're dealing with likelihoods here, right? So what is the likelihood given inputs that we will get a specific output? We're not getting certainty. We're getting, this is what the computer thinks given the input data. So we can, and with unsupervised machine learning, which we'll cover after the break, we're going to see how can we spot patterns in the data, and can we start building some hypotheses? So yeah, absolutely. And can I share data cleaning scripts with us too? Yeah, well, I'll be sharing that. I'll be sharing the scripts as part of on the GitHub after the session is all done. So with that, I know I've cut 3 minutes into everybody's break. So I think, Ethan, let's call a break until what? We were supposed to break until 3:30?
We were. Do you want to say 3:35?
I don't want to cut too much into, yeah, let's do 3:35 and we'll wrap, and we're slated to wrap at 4:30, right?
On the event, it is till 4:45, so we will see where we get to.
Oh, okay.
Come 4:30.
Okay, cool. So yeah, we'll do our best to fit as much as we can in. So yeah, let's break until 3:35.